Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at something called formal charge, resonance, and bond order. So this is going to come after we review how to write Lewis dot structures the right way. And this just takes it a step further. We're going to look at some of the details about those Lewis structures that we're drawing. We're going to see sometimes there's more than one possible correct structure, but one of them is more preferred. One of them is a preferred structure compared to some of the other ones. We'll figure out which one is that. We'll take a look at something called resonance, which is also something to do with your Lewis dot structures and maybe if it has double or triple bonds, and something called bond order. All right, so let's take a look at what these are. So a few molecules can result in several possible correct Lewis structures. So sometimes it'll specify to just draw or write a correct Lewis structure, or which one is the best Lewis structure. So if you want to see which one is the most correct, I guess, or the preferred structure, we're going to need to determine something called the formal charge on each atom in the molecule. That'll help us determine, again, which is the most probable structure. So here's your formula for formal charge. Sometimes I don't even really worry about some of the exact terms here. I'll show you how to do it really easily in just a second here. So formal charge is what it sounds like. It's the formal charge on an atom. So it's broken down into two parts. So atoms have valence electrons that they're supposed to have. Like carbon's supposed to have 4 valence electrons. And then we're going to see how many does it actually have in the Lewis structure. How many electrons are actually assigned to it? Okay. What are assigned electrons? They're all the unshared electron pairs and half of the bonded electrons. So some students get confused by this, but don't be. I have two pictures here. So these are two structures that are technically correct for carbon dioxide, for CO2. So the one on the left, you'll recognize is the preferred structure. Well, why is that? So we'll find out why in a second here. And the one on the right is still a valid structure. You're just not going to see this one as the preferred structure. So the one on the left, you have carbon in the middle, 2 oxygens, one on each side. Let's find the formal charge. And I mean, it's already written here for you. Let's see how we calculate that. So oxygen, and both of these will be the same because they're the same bonding structure here, right? Number of valence electrons. Well, how many valence electrons does oxygen have? It has 6. Okay? We want to subtract the number of assigned electrons. How many assigned electrons does it have in this structure? Lone pairs only belong to the atom that they're on. Okay, so oxygen has 2 lone pairs. Those are 4 electrons. They belong 100% to oxygen only. But if you look at this double bond that's here, I have these little red squiggles that go through it to show us that half of that double bond we're going to assign, assigned electrons. Half of that double bond we're going to assign to oxygen, and the other half we're going to assign to carbon. Okay, so if we look at what our assigned electrons are, we have 4 of them from the lone pairs. Okay, so there's 4 there. In addition to the half of the bonded electrons. So in a double bond, you have 4 electrons, right? Half of that is 2. So 4 plus 2, okay? So you get 6 minus 6 gives you 0. So the formal charge on that oxygen is 0. So it should have 6 valence electrons. It's assigned 6 valence electrons in the structure. Formal charge is 0. Okay? Same thing with the oxygen over here. Carbon, though, is also a formal charge of 0. Let's see why. Valence electrons, we have 4. We're supposed to have 4. Minus your assigned electrons. So unshared electrons, so lone pairs, I don't see any, so it's 0. Plus half of the bonded electrons. So carbon has 1, 2, 3, 4. It has really 4 bonds on it, right? You have a double bond over here, double bond over here. So on the double bond on the left, that's 4 electrons, but half of them belong to carbon. The other half, remember, belong to oxygen. So we get 2 here. Okay, and we also have the same situation over here. So we have a double bond. It's 4 electrons. 2 of them are assigned to carbon. So 2 assigned over here, 2 assigned here, so that's 4. Okay, 4 minus 4 is 0. So the formal charge on carbon here is 0. All right. Over here on the right, we're going to look at this other Lewis structure, structure B. So oxygen on the left is the same as the ones over here on structure A. So formal charge is 0. I'm not going to recalculate that. In the middle, though, we have our oxygen atoms. Formal charge is +2. How do we get that? Well, we have 6 valence electrons that we should have. And then our assigned electrons, we have no lone pairs. And we have a double bond, so there's 2 electrons assigned from that. Because remember, the double bond here is 4 electrons, but 2 of them are assigned on this oxygen. The other 2 are assigned on the middle oxygen. So 2 are here. Okay. Same thing, other side, we have a double bond. 2 electrons are assigned to that oxygen, so 2 and 2 is 4. All right, 6 minus 4 is 2, which is why our formal charge is 2 here. Carbon on the right, we have a formal charge of -2. How do we get that? Carbon has 4 valence electrons minus the assigned electrons. So we have all the lone pairs, the unshared electrons. We have 2 electrons here, 2 electrons here, so that's 4 there. And the half of the bonded electrons, we have a double bond on carbon. Half of that is 2. All right, so we have 4 minus 6 gives you -2. Okay, so formal charge on carbon here is -2. It should have 4 valence electrons. It really has 6. 1, 2, 3, 4 from the lone pairs, and 1 from this part of the double bond, and 1 from this part. What students eventually end up doing is they don't go through all this work. It's a big waste of time. Like, okay, carbon has 4, so in my head I say 4. Should have 4 valence electrons. 4 minus 1, 2, 3, 4, and each bar, because each bar is, or each dash is 2 electrons, so you want half of that. So each bar is going to represent 1 assigned electron. Okay, so 1, 2, 3, 4, 5, 6. 4 minus 6 is -2. Oxygen in the middle. 6 minus 1, 2, 3, 4. 6 minus 4 is 2. Easy. All right, so you go through it pretty quick. You want to find the formal charge on each of these. So take a minute and go through it, and we'll write down the formal charge on each of these. So you can pause it, try to give it a shot, and then we'll see what we get. Okay, so structure on the left here, we have 3 basically different Lewis structures for NCS -1, just an ion that we have. So over here we have nitrogen, should have 5 valence electrons, and assigned electrons are 1, 2, 3, 4, 5, 6, and 1 from that bond is 7. So 5 minus 7 is -2. Carbon should have 4 minus 1, 2, 3, 4. So that gives us 0. Remember, carbon has 4 bonds on it. That's 8 electrons. Half of that is 4, so 4 minus 4 is 0. And then the sulfur should have 6. 6 minus 1, 2, 3, 4, 5 gives you a +1. Okay, structure in the middle. Nitrogen should have 5. 5 minus 1, 2, 3, 4, 5, 6 gives us -1. Carbon should have 4 minus 1, 2, 3, 4 gives you 0. Sulfur is 6 minus 1, 2, 3, 4, 5, 6 gives you 0. Off to the right, nitrogen should have 5. 5 minus 1, 2, 3, 4, 5 gives you 0. Carbon is 4 minus 1, 2, 3, 4 gives you 0. Sulfur is 6 minus 1, 2, 3, 4, 5, 6, 7 gives you -1. Okay, so which one of these is the most correct structure? If you went all the way back to the previous slide, you know that the structure A is the more preferred structure for CO2. What do you notice about the formal charges? They're all 0. Here, it's not very preferred, so you have a charge of 2 and -2. So here, which one of these is a preferred structure where your formal charges are 0 or close to 0? Well, it's not going to be this one, right? Because you have a 2, 1, or a -2, 0, and a 1. Here you have -1, 0, 0, and then 0, 0, -1. What you want to do when you have a situation like this is you basically have a tie here between these two structures. What you want to do is figure out which one of these has the -1. Okay, that's our one that's on a different atom here, right? Figure out between nitrogen and sulfur, which one of those two atoms would prefer to have a negative charge? Well, it's going to be which one is more electronegative, right? If something is very electronegative or higher on the electronegativity scale, it is okay with having that electron. That want for an electron is pretty strong. Nitrogen is definitely higher than sulfur. Nitrogen is one of our top 3. So nitrogen would better handle that -1 charge than sulfur would. So that's going to negate that structure. This will be your more preferred structure right here. All right? So the sum of the formal charges must equal 0 unless it's an ion. So back here, these were all ions. It was a -1 charge. So your formal charges should add up to -1. They do. -2 and 1 is -1. -1, 0, 0 is -1. 0, 0, -1 is -1. If you went back to CO2, this formal charge is added up to 0. CO2 is neutral. Okay, I already went over the second point here. If multiple structures are possible, you choose the one with the lowest formal charge. So something like +1, 0, -1 would be preferable to 3, -1, -2. And if the formal charges are the same, the atom with the higher electronegativity would be preferred in terms of your Lewis structure, right? So the one with the higher electronegativity should have the negative formal charge on it. And that was the case on the previous example. The negative formal charge could be handled better by nitrogen, so that one is the more preferred structure. Right, so back to what we just did, both have the same formal charge. In terms of the two structures on the right, N is more electronegative, so it can handle it better. So there you go. Okay, take a minute here and try to write 3 possible Lewis structures for the cyanate ion, which is NCO negative. Use the formal charges to predict the most plausible structure. Okay, so let's take a second and do that, then we'll go over those. Okay, here you go. These are your 3 that you should have ended up with. Really can't come up with more than this if you follow your octet rules and your Lewis dot structure rules. So if you look at what we end up with here, here are our 3 Lewis structures. If we assign formal charges, we have a formal charge of 5 minus 1, 2, 3, 4, 5, 6, 7. So we have a -2. We have a 0. And it looks like we have a 1, 2, 3, 4, 5. Looks like we have a +1 here. This Lewis structure, we have 1, 2, 3, 4, 5, 6. We have a -1. We have a 0. And we have 1, 2, 3, 4, 5, 6. We have a 0. And here we have 1, 2, 3, 4, 5. So 0, 0, and 1, 2, 3, 4, 5, 6, 7, -1. Okay, this makes sense. They're all -1 ions, so your formal charges should add up to -1. They do here, here, and here. So we're down to, this one's not going to work. We're down to the 2 structures on the right. Which one of these would be preferable? You want to look at, well, where's my -1 formal charge? Here it's on N, here it's on O. Which of those 2 atoms, nitrogen or oxygen, could better handle that negative formal charge? If you look at your periodic table and you remember your electronegativity rules, N, O, and F are the top 3. Nitrogen is a little bit less electronegative than oxygen. Oxygen is a little bit less electronegative than fluorine. So oxygen has a higher electronegativity. There you go. That's your answer. This one's still, it's still plausible for this to occur, right? I mean, nitrogen and oxygen are pretty electronegative, but this is definitely your preferred structure. All right? Keep in mind here, if it just asks you for a correct structure, period, then any of these 3 will work. If it asks you for the best possible Lewis structure, the only answer is the one on the right. Okay? Don't do extra work. Pay attention to what's given to you in the problem. Is a valid Lewis structure all they want? All of these work. They all follow the rules. If it's the best one, though, you got to go through the formal charge process. Okay, moving on to the next topic here, which is resonance. We're going to look at O3. Ozone is like the best one to look at resonance for. So here's your Lewis dot structure of O3. Okay, you may have drawn this with the double bond on the left, and that's what we're going to get to here. All right. So what we want to do is use our chart earlier in your note sheet where you have bond length. We want to predict the oxygen-oxygen bond length in the molecule. So if you went back in that chart, you would have a bond length for OO single bond and a bond length for OO double bond. And you would notice that they're different. Even without looking, because I don't have it in front of me, I know that the oxygen-oxygen single bond has a longer bond length than the oxygen-oxygen double bond. Single bonds are the longest, then double bonds are a little bit shorter, and triple bonds are the shortest. Okay, so you could write them in, but we're going to be changing that in a minute here, so you might not really want to bother with that. If you look at ozone experimentally, and you determine the bond length experimentally, you would actually notice that the bond length is equal for both of those bonds, even though the chart tells you that they're different. Okay, so why is that? The bond length comes out to 1.278 angstroms. And if you look at it, this gives you some electron density. You would think that there'd be more electron density over here with this double bond, right? Or maybe even like you'd see a little patch of it higher over here with this, the 6 lone pairs versus the 2 lone pairs over here. But if you notice, this is the ozone, electron density like image here. You notice it's exactly symmetrical. It's the same. Looks like you have a high level of electron density here and a low level of it up here where that top oxygen would be. Okay, so why is that? Why do we experimentally get the bond length to be equal? We could figure out bond length based on, really one way to do it is to see how much energy it takes to break bonds and go from there. But you don't really need to worry about that too much right now. But notice that they are the same length. That tells us then this really isn't the right structure, okay? If it was the right structure, we would get 2 different bond lengths here, but that's not what we have. So what does this mean? It means we have 2 bonds that must actually be the same type of bond. We cannot accurately represent ozone with a single Lewis structure though, all right? So what we're going to actually have is something between a single and a double bond. All right, so if you look at there you go. Look at the structure here. You have the structure on the right. That's the first one that we had on the previous slide. You can also draw the structure like I have here on the left. Let me see if I can make that text go away for just a second here. Both of these are obviously valid Lewis structures, and they're really the same Lewis structure. All we're doing is moving the double bond over. We still have the same structure, right? We have one OO double bond and one OO single bond. Same over here. An OO double bond and an OO single bond. Same structure. How are they, why are they related though? What does this mean here? A double bond has something called delocalized electrons. And I may have mentioned delocalized electrons previously, but if I haven't, it means that they're not, localized means kind of like located in one specific area, all right? Delocalized means it's not, right? So they can move around a little bit. So what you're going to do is have the electrons in that double bond bounce back and forth between these, okay? So you're going to end up with this double bond, like these 2 electrons here, bouncing over here, here. Okay, they're going back and forth a million times. So you really have a combination of these 2 structures, okay? The actual bond is between a single and a double bond. Okay, let me get rid of that mess here, okay? So this is kind of interesting because we don't really have, in reality, we don't really have a double bond and a single bond. We have something between that. So what type of bond do you think we really have here? Well, we actually have, if you want to think of it as a single, like a 1.5 bond, a 1.5 bond, not a single bond, not a double bond, but the average of that, 1.5 bond, okay? If you look at the bond length, if you went back and you saw that bond length, the bond length that you can calculate here is between a single bond and a double bond, okay? So it's shorter than the double bond, but it's bigger than the double bond. Okay, it's shorter than the single bond, bigger than the double bond. So when you have to draw a Lewis structure for something like ozone, where it has a resonance, you have to draw one of your structures, a double arrow, and then your other structure, and then potentially more of them. Okay, so this will make you go crazy. Notice how the delocalized electrons move the double bond in pink in these 2 benzene rings. So there's 2 benzene rings connected, right? Benzene, this is just a carbon chain here, or a cyclical carbon chain. And all the corners are where carbons are located, all right? And there's some double bonds there. They always move around. So on your paper, you obviously have to draw it one way, right? Like I have to draw one Lewis structure like this and one like this to show that there's resonance. But just know that, in reality, it's just one structure with those electrons moving around. Okay, it's kind of hard to explain this because we have to draw the structures because we can't draw the electrons moving like this. Okay, we're not going to draw it, then erase it, draw it, then erase it. That's the dumbest thing I've ever heard of. So you have to do, you have to have that notation like on the previous slide. So just like green is a synthesis of blue and yellow, ozone is really just a synthesis of the two structures. So in reality, it's these two structures that are resonance structures, like thrown in a blender, and you have your ozone molecule where you have that 1.5 bond, those electrons moving around, those delocalized electrons moving around, just like blue and yellow gives you green. All right? Oops. So note that in order to be resonance, they have to be identical formal structures. Students make this mistake all the time. Once I teach resonance, they go crazy with resonance on everything. Cannot do that. If you write the formal charges above the oxygens, you'll notice that they're the same on both structures. So we have 1, 2, 3. We have a formal charge of 0, formal charge of 1, 2, 3, 4, 5, a positive 1, and a negative 1. Notice how we add up to 0 because it's a neutral structure. Same thing over here. Our negative 1 is here, our positive 1 is here, and our 0 is here. Okay? Formal charges are identical. Be on the lookout for resonance if you're finding a double or a triple bond, okay? And it's usually where you have something like this, where you have your central atom and then the branching atoms are the same. Like here, you could think of your oxygen as your central atom, and you're branching off oxygen, oxygen, okay? It's not going to work too well or very easily if you have different atoms branching off of that central atom, okay? So take a second, draw the Lewis structure for HCO2 negative, and let's see if we could figure out if it has any resonance structures or not. Okay, so you can look at HCO2 negative, and you can draw these two structures, and you can notice that we do have some resonance structures here. In reality, because you have the central atom here as your carbon, you can have your double bond on this oxygen or your double bond on this oxygen that you have down here. So this double bond can bounce back and forth between those two atoms. Okay? So we draw the resonance this way. In reality, it is one structure with not a double bond here and a single bond here, or a single bond here and a double bond here. The bond character of this carbon-oxygen bond, this region, is 1.5. Okay, it's like a 1.5 bond in reality. So those electrons are constantly bopping back and forth. Okay? So that part of the double bond, that's your delocalized electron group. Okay, and that's what I have here for you. Oops. Okay, so how many resonance structures can be drawn for nitrate? I didn't want to have it pop up. There it is. So there's our 3 resonance structures for nitrate. You can see that we have our double bond in 3 different locations. All right. So it's not like we have a double bond, a single. In reality, put these 3 resonance structures in a blender, blend them all up, and whatever you get left over with, that's the general structure you have. Okay. So the bond character here is going to be even different, okay? So it's going to be, again, a combination of, it's going to be somewhere between a single and a double bond, but you're actually going to end up with like a 1 1/3 bond, okay, for this. Because it's going to be primarily single bond character because you have 2 single bonds and 1 double bond, okay? So it's not like the last one where you're going to have like a 1.5 bond. This one's a little bit less than a 1.5 bond character because there's more single bonds here than double. Okay, to wrap it up, we're going to look at bond order, which is exactly what I referenced as I was going through the resonance portion of this lecture. So in most cases, it's the same thing as the type of bond. So single bond is a bond order of 1. It's telling you the characteristics of that bond, right? Like I went over here, you really have a 1.5 bond, right? So we would say our bond order for this section here is 1.5, okay? We're going to formally figure that out here. To find the bond order, take the number of dashes, which is the number of bonds, divide it by the number of domains, and you're going to have your bond order. So here, how did I come up with the answer that I did? Take your number of dashes. For each of these, you have 4 dashes, divided by number of domains, that is 3. And that's exactly what I said you end up with. This is 1 1/3. Okay, so the bond character, the bond order here, is like I have 3 1 1/3 bonds. It sounds ridiculous, okay? But if you looked at the bond length, it's closer to that of a single bond between N and O than it is for a double bond between N and O, because the bond character is 1 1/3. All right? So in the case of resonance, like, only worry about this with resonance, okay? Another example of students just going nuts when I teach bond order is they apply it to a million things where it doesn't apply, all right? So make sure you only apply it when asked. Usually if you're trying to determine bond length, okay, where you have resonance structures. I cannot highlight that enough. Resonance structures are where this comes into play. That's why I did it after I lectured on that. So in the case of resonance, the bond order is somewhere between the bond types. I already went over that. Let's look at the bond order for water, ozone, and nitrate. Okay, so here they are. For water, bond order is number of dashes, which is 2, divided by domains. And here we have 1, 2. Okay, the lone pairs don't take part in this because they're not bonded. Okay. So, okay, number of bonded domains. That is really important here, okay? So it's not domains in general. You're going to get all sorts of messed up. It is bonded domains. So we have 2 bonded domains. Bond order of 1. Okay? I didn't even really have to bother looking at this. I'm not even going to bother calculating that because I'm like, okay, what's my bond order? Well, I have a single bond and a single bond. Well, okay, that was easy. If I only have single bonds, my bond order has to be 1. It has to be a single bond order, characteristic of a single bond. Okay? Look at ozone. Ozone, I already went over this, but ozone is going to be a little bit different. I have a double bond and a single bond. So the bonds are different, okay? So I'm not going to have a bond order of 1 or a bond order of 2. This whole structure is going to have what bond order? Look at your domains. Or I'm sorry, look at your number of dashes. It's 3. Number of domains, that's bonded domains is 2. 3 over 2 is 1 1/2. Okay, so my bond order here is 1.5. Over here, for the nitrate ion, I already did it. Number of bonds is 4. Domains that are bonded, it's 3, so you get 1 1/3. Okay, so that's our bond characteristic for that. Just some other things to wrap up in terms of, that's it for bond order. Other things to wrap up in terms of just notation. If you see something like this, an organic chemistry notation, every angle is a carbon. So you have a carbon here, here, here. You get the point. Hydrogens are not shown. So over here, there's a carbon there, okay? And that carbon has a double bond and a single bond. So you're still missing out on another bond on that carbon. So you could picture a hydrogen here. Okay, they don't show it because it gets too cluttered. If you take organic chemistry, you'll draw a trillion of these, and you'll understand this in the first 5 minutes of organic chemistry. But if you see these structures, know that carbons are the angles, hydrogens are not shown, but they're branched off wherever you need to fill in more bonds for your carbon. All right. Benzene is another example with resonance. So You can draw a benzene ring like this. It's a lot of work and it's very cluttered and semi-confusing. Another way to draw it is like this. This is one where you had the pink double bonds moving around like crazy earlier in the presentation. You can also draw it like this. You'll see me do it more so like this, but this is another quick way to show that. Okay, another example of an organic compound is cholesterol. So again, all the corners here, all the angles are carbons, and you have different functional groups that you'll eventually get to. If you took AP Bio, you know all about functional groups. If you take organic chemistry, you'll learn all those within the first week. Okay, just some other examples of DNA and RNA. Okay, so you might recognize some of these. Okay, guys. Long lesson on all of this. A lot of information. If you have any questions, let me know in class when we talk about it. There's some practice in your packet that you'll do, and we'll figure it out from there. All right, thanks, guys.